Hello, everyone, and welcome to today's Journal Club. I'm presenting a fascinating systematic review published in 2025 by Rahmani and Sharifi titled Urban Heat Dynamics in Local Climate Zones. This paper provides a diagnostic review of how different urban morphologies drive heat accumulation and what mitigation strategies actually work. As our cities continue to grow and climate change intensifies, understanding the thermal anatomy of urban environments has never been more critical for public health. Let's start with the problem. The authors frame urban heat using a medical metaphor that's quite instructive. First, we have the symptom. Rapid urbanization amplifies the urban heat island effect, directly increasing morbidity and mortality risks. Second, the diagnostic tool, the local climate zone framework, which provides a standardized 17-class system to categorize urban thermal environments. Third, the diagnosis itself, LCZ A, or compact mid-rise zones, consistently act as the city's furnace, while LCZ A high-rise zones present a paradox, and LCZ A is the coolest built zone. Finally, the prescription, morphology-specific mitigation strategies, including ventilation for dense zones, cool roofs for industry, and green infrastructure as a universal solution. The urgency becomes clear when we look at the projections. By 2050, we're facing a surge in global urban population that will intensify land use changes. This slide beautifully illustrates the mechanism. Urbanization drives the decline of green space and proliferation of impervious surfaces, which in turn raises surface and air temperatures. The consequence is rising heat-related cardiovascular and respiratory illnesses. The key insight here is that we must understand the city's spatial anatomy, not just treat it as a thermal monolith. Different neighborhoods experience fundamentally different heat dynamics based on their built form and surface properties. This brings us to the Local Climate Zone Framework, developed by Stewart and Oakey in 2012. It's a game changer for urban climatology because it provides a universal language for comparing thermal performance across different cities and climates. The system classifies environments based on three key attributes: building height, packing density, and surface cover. On the left, we see built types, LCZ 1 through 10, ranging from compact high-rise to heavy industry. On the right are land cover types, LCZ A through G, from dense trees to water bodies. This standardization allows researchers worldwide to communicate findings in a comparable framework, which is essential for developing evidence-based urban planning policies. The authors conducted a rigorous systematic review, starting with 812 studies from multiple databases. After screening and filtering, they included 154 studies in their analysis. One of the most revealing findings concerns the measurement divide. The vast majority of studies, 68.8%, used surface urban heat island measurements from satellites, essentially measuring the skin temperature of the city. Only 33.1% measured canopy urban heat island, the air temperature that humans actually breathe. Critically, only 7.1% of studies combined both methods. This measurement gap is important because surface and air temperatures can tell quite different stories about human thermal comfort and health risks. Now let's look at the key results. The authors identified three primary offenders for extreme heat. First is LCZ 2, compact mid-rise zones. These are consistently the hottest in both surface and air temperature measurements. The culprit is high building density that blocks wind, combined with lack of height which prevents adequate shading. Second is LCZ 10, heavy industry zones, with high anthropogenic heat emissions from industrial processes and vast concrete expanses. Third is LCZ 8, large low-rise zones, characterized by extensive asphalt surfaces, like parking lots with zero vegetation. These are essentially heat traps that absorb solar radiation all day and release it slowly at night, preventing nocturnal cooling. Perhaps the most counterintuitive finding is what the authors call the high-rise paradox. During daytime, tall buildings provide protective shading, blocking solar radiation and lowering surface temperatures at street level. However, at nighttime, these same buildings create what's known as the canyon effect. Deep street canyons reduce the sky view factor, meaning heat absorbed during the day becomes trapped, preventing nocturnal cooling. The geometry that protects during the day becomes a thermal prison at night. This finding has profound implications for urban planning, suggesting that high-rise development isn't inherently good or bad for heat, but requires careful consideration of street width, building spacing, and orientation. In contrast, three local climate zones emerge as thermal refuges. LCZ A, dense trees, is nature's air conditioning, providing the highest magnitude of cooling through evapotranspiration and shading. LCZ-G, water bodies, act as significant thermal buffers due to water's high specific heat capacity. And LCZ-9, sparsely built zones, consistently rank as the coolest inhabited zone because low building density and ample spacing allow for airflow and heat dissipation. The small chart shows the frequency distribution, confirming that LCZ-A, G, and 9 consistently appear as the coolest zones across temperature measurements globally. This evidence base provides a strong argument for preserving and integrating these zone types into urban planning strategies. The authors synthesized the thermal drivers into three categories. First, morphology, or the shape of the city. Inefficient layouts block ventilation, while deep urban canyons trap radiation. Second, surfaces, essentially the skin of the city. Low albedo materials like dark asphalt absorb solar energy, while impervious surfaces prevent evaporative cooling. Third, ecology, the lungs of the city. Low vegetation fraction reduces shade and transpiration, two critical cooling mechanisms. This triad of morphology, surfaces, and ecology provides a diagnostic framework for understanding why certain zones overheat. Importantly, it also suggests three distinct intervention pathways for mitigation. This leads directly to the paper's mitigation framework, which emphasizes zone-specific interventions. For compact zones, LCZ 1 through 3, the driver is high density and low airflow, so the solution is morphological intervention. Regulate densification and optimize openness to create ventilation corridors. For industrial and low-rise zones, LCZ 8 and 10, the problem is high imperviousness and low albedo, so the solution is material intervention. Deploy cool roofs and permeable pavements to increase reflectivity and allow evaporation. And critically, there's a universal intervention that benefits all zones: increase green infrastructure. Trees, green roofs, and vegetated corridors provide cooling benefits across all urban morphologies through shading, evapotranspiration, and improving the microclimate. The beauty of the LCZ framework is that it allows for context-specific solutions. The authors present two contrasting case studies. In compact high-rise cities like Tokyo or Shanghai, the challenge is blocked airflow. The solution involves creating ventilation corridors, wind paths through the dense fabric, and vertical greening on building facades. In contrast, arid or desert cities like Phoenix or Las Vegas face the challenge of barren, paved heat from LCZ-E surfaces. Here, the solution emphasizes shade structures and water features, though importantly, irrigation-heavy grass is less effective in water-scarce environments. This regional specificity is crucial. There's no one-size-fits-all solution. Urban heat mitigation must be tailored to the local climate zone composition and regional climate context. Now we come to a critical limitation identified by the authors: the data gap in the global south, particularly in Africa. The research bias is stark. The majority of urban heat island research focuses on the global north, with the city type chart showing dominance of large city studies over other classifications. Meanwhile, Africa's rapidly urbanizing informal settlements present a classification challenge. These areas feature high density, combined with unique materials like scrap metal and tin roofs, plus irregular layouts that don't fit standard LCZ 1 through 10 definitions. The result is underestimated risks for vulnerable populations. The authors argue that extending the LCZ framework to better capture these informal settlement morphologies is essential for climate justice and effective heat mitigation in the regions that need it most. So what are the implications for planetary health? The paper makes three key recommendations. First, precision planning. We need to move from general citywide warnings to targeted interventions based on LCZ mapping. Second, direct action. During heat waves, cooling centers and emergency services should be specifically deployed to LCZ A, compact mid-rise, and LCZ 10 heavy industry zones, where vulnerable populations face the highest exposure. Third, integration. We must combine LCZ thermal data with demographic data for comprehensive heat health risk assessments. This integration would identify not just where it's hottest, but where the hottest zones intersect with elderly populations, low-income communities, and other vulnerable groups. This is the path toward thermal equity in our cities. The authors outline 3 critical research priorities for the future. First, hybrid data collection, combining satellite surface temperature measurements with ground-level canopy, air temperature measurements for human-centric accuracy. This would bridge the measurement divide we discussed earlier. Second, refined classification, developing LCZ subclasses specifically for informal settlements and adaptations for the Global South. This would make the framework truly universal. And third, longitudinal tracking, monitoring the long-term effectiveness of mitigation strategies. We need to move beyond before and after snapshots to understand how interventions perform over years and decades, accounting for climate change, urban growth, and maintenance realities. This evidence base will be essential for justifying continued investment in urban heat mitigation. Let me conclude with the central argument from Rahmani and Sharifi's systematic review, beautifully captured in this final slide. The LCZ framework provides a diagnostic grammar for reading urban heat landscapes, giving us a common language to identify and classify thermal zones. In our Johannesburg investigation, this framework proved essential for understanding the city's complex thermal anatomy at the neighborhood scale. So we've just explored the systematic review by Rahmani and Sharifi, which established the LCZ framework as the diagnostic tool for reading urban heat landscapes. Now I want to show you how we're testing this framework in practice, specifically in Johannesburg, South Africa. This represents a pilot investigation, a reverse urban heat island analysis for the greater Johannesburg metropolitan region. We're using peak summer data from January 15th to February 14th, 2025, sourced from ERA5 Land Climate Reanalysis. The title gives away the surprising finding, Johannesburg's Cool Heart. But before we jump to conclusions, remember this is a preliminary exploration with 1 month of summer data. What we're really testing here is whether the LCZ framework can generate actionable insights for African cities, where this approach has been underutilized. The findings themselves are tentative and may look completely different during Johannesburg's cold, dry winter season. Let me walk you through how this analysis was done. It's a powerful combination of human expertise and machine learning. For the LCZ classification, we used the global LCZ map created through the WOOD-APT initiative. This combines 2 inputs: human digitized training areas from Google Earth, experts identifying this is definitely compact high-rise, this is definitely scattered trees, and Landsat 8 spectral data showing what the satellite actually sees. A random forest machine learning algorithm learns from these examples and classifies the entire city. Think of it as teaching a computer to recognize urban forms the way a human expert would. For the climate data, we used ERA5 Land Reanalysis from the European Center for Medium-Range Weather Forecasts. This combines millions of weather observations with atmospheric physics models to give us hourly temperature at every point on Earth. We sampled 10 locations across Johannesburg's urban to rural gradient. Here's what made this analysis feasible: Google Earth Engine. We extracted 7,200 temperature observations, 30 days, 24 hours per day, 10 locations, in just 46 seconds, using the Python API. Without cloud computing, downloading and processing this much satellite data would take hours or days. Earth Engine brings satellite data analysis from the research lab to the classroom. All statistical analysis was done in R using the LCZ4R package, specifically designed for local climate zone research. This open source approach means anyone can replicate our findings. Now let's zoom into central Johannesburg to see the urban mosaic revealed by our LCZ classification. The CBD appears as that dark red compact high-rise zone in the center, the iconic downtown skyscrapers that define Johannesburg's skyline. Just to the north, Sandton presents another compact high-rise and mid-rise cluster, functioning as a second CBD with its modern office towers. Between them, Rosebank emerges as a transitional zone mixing compact and open mid-rise development. To the west, Soweto displays a distinct mosaic of compact and open low-rise residential areas, a morphological signature reflecting decades of urban development history. What's critical for our thermal analysis is observing how these vegetated zones, shown in green, penetrate throughout the built-up areas. This spatial distribution of green fingers helps us understand the potential cooling corridors and thermal refuge zones within Johannesburg's urban fabric. The LCZ framework allows us to connect these morphological patterns to their thermal behavior. This side-by-side comparison perfectly illustrates the morphological contrasts we're investigating in Johannesburg. On the left, the CBD and Sandton represent the economic engines, compact high-rise, LCZ1, and mid-rise, LCZ2, zones, dominated by dense built form, with minimal green space. On the right, Soweto, home to over 1.3 million residents, shows a dramatically different LCZ composition. Here we see open low-rise residential development, LCZ 6, the characteristic township housing pattern. But notice the crucial detail: even within this high-density residential area, green patches and scattered trees are distributed throughout. This vegetation, though modest, plays a significant role in the local thermal environment. Key neighborhoods visible include Orlando, with its iconic Orlando Towers, Deep Kloof in the center, and Meadowlands to the north. That large structure is FNB Stadium, the 2010 World Cup venue. What's important for our investigation: Soweto's predominantly open, low-rise LCZ types with scattered vegetation contribute to more moderate temperatures, contrasting sharply with the compact built zones in the CBD. This morphological difference translates directly into thermal equity implications for Johannesburg's residents. This chart quantifies what we observed visually in Johannesburg's LCZ distribution, and the results are striking. The dominant zones are low plants, LCZ-D, and dense trees, LCZ A, together accounting for over 50% of the metropolitan region's surface area. This is remarkable. Johannesburg is a major African city, where more than half the land is vegetated natural cover. Now looking at the built environment types, open low-rise, LCZ 6, at 44.1%, represents the largest built category. This is predominantly Soweto and similar township areas we just examined. Dense and compact low-rise zones add another 26%, showing the prevalence of low-rise residential development across Johannesburg. Here's the critical finding. Notice that compact high-rise, the iconic skyline image of Johannesburg's CBD, covers a tiny percentage despite being the city's most recognizable feature. This LCZ composition is essential for interpreting our temperature results. The majority of Johannesburg consists of vegetation and low-rise development, with limited compact built zones. Understanding this baseline helps us identify where thermal inequities emerge and why certain neighborhoods experience such different heat exposures. Now for the critical thermal data from our Johannesburg investigation. This graph reveals a surprising finding that challenges conventional urban heat island expectations. The diurnal temperature patterns show all location types, peri-urban, rural, suburban, and urban core, following remarkably similar cycles throughout the day. Everyone experiences the morning minimum around 6 a.m. at 15-16 degrees C, then peaks around 2 to 3 p.m. at 25-28 degrees C. Here's the unexpected finding. Notice how tightly grouped these lines are. They're nearly parallel. The urban-rural temperature difference is only 1 to 2 degrees C on average, which is much smaller than the typical urban heat island effects reported in other cities. The standard UHI is around 7 degrees Celsius. This is our first hint that something unusual is happening in Johannesburg's thermal landscape. Rather than seeing the expected strong urban heat island with significantly elevated temperatures in the CBD, we're observing a minimal gradient across the metropolitan region. This finding sets up the critical question. If Johannesburg doesn't follow the typical urban heat island pattern, what thermal dynamics are actually at play? This is where our reverse urban heat island analysis becomes essential.